Welcome everyone. My name is Robert Hodges and I'll be your host today at our webinar on high reliability data loading on ClickHouse. It's my pleasure to welcome my friend and colleague Alexander Zaitsev, who's CTO of Altinity and an expert on this topic. So he'll be running the presentation, which will start in just a second. Let me just tell you a couple of things about the webinar software we're using that will help you enjoy the presentation. First, we are recording this webinar and we will send links to both the recording as well as the slides afterwards. You'll get that as in an email because you've signed up. The second thing is that there's a question and answer box in that's available through the webinar control panel. If you have questions, feel free to just type them into the box. We can answer some of them in background and we should have time at the end to answer more questions. So please go ahead, feel free to answer any question you like about this topic and we'll answer them as effectively as we can. The final thing is that at the end of the webinar, we will run a very brief poll, which asks 3 questions. It takes about 15 seconds to fill out. It's just basic information about level of webinar, future topics, things like that, that help us make these webinars better the next time we present them. So with that, thank you very much for attending. I'd like to turn it over to Alexander Zaitsev. So take it away, Alexander.
Thank you, Robert. Today, we'll talk about ClickHouse inserts and high reliable data ingestion. This is a topic that appears pretty regularly in different community channels, GitHub issues, in our support experience. And because ClickHouse is an analytical database, it has some somewhat non very traditional guarantees on consistency. And understanding those and using ClickHouse features properly is a must for reliable systems. Let's start with a very simple example. Consider we have an event stream that is being inserted into your ClickHouse database. So you expect that once insert is completed, then your data is in ClickHouse. And this is almost right. But there are more different moving parts involved. In particular, there is OS level page cache, and ClickHouse, it turns out it never does fsync. So if your data is inserted, it doesn't mean that your data has reached the storage. So potentially, if your ClickHouse crashes right after your insert has been succeeded, then you may lose your data. It gets a little bit more complicated if you have materialized using ClickHouse. So when you insert the data, it goes to the table, then you have multiple materialized, you may have multiple materialized views attached, you may have cascading materialized views. They all start writing data to their underlying tables. And what happens if your insert is interrupted in the middle? Do you know? It's not as easy as it seems. If you have distributed table or distributed system with multiple shards, you typically, your single insert, it goes to a single shard, even if you write to a distributed table. And only later on, in the background, the data is being sent or fetched to other shards. And what happens if there is a failure somewhere in the middle? What happens with your data? Do you have it consistent or not? Let's add replication to the picture. By default, replication in ClickHouse is asynchronous. So once you inserted the data, it doesn't mean, even if you have replica or multiple replica, it doesn't mean that the data has been inserted to all replicas. And if there is a failure after you inserted the data and your box has dead, what happens to your data? These are all questions that we're going to discuss today, and also what we can do in order to get some consistent guarantees. So we will discuss performance first, because we definitely want our inserts to go as fast as possible. So what is important for performance? Reliability, and our goal is to make sure that once the data has been inserted, It is in the server and we can access it and it's never lost. And also there is a topic of deduplication, which often comes in discussions because you can retry and insert if something failed, right? But how can you be sure that your data has been inserted only once and not twice or more times? This is not a trivial topic for ClickHouse, apparently. So let's start with performance first. And in order to understand what is important for performance and how we can tune a system for the optimal performance, it's important to understand what happens under the hood when the data is being inserted to a single ClickHouse server and a single table. So ClickHouse does several steps when processing the data. The data itself, when you insert it through HTTP interface, for example, or from files, it is coming by rows. This is a natural format from data sources. So ClickHouse parses those rows of the data and converts the data to internal structures, which are columns. So internally, ClickHouse being a columnar database, it stores everything in columns. Then it splits columns into partitions and parts based on the table definition. So potentially a single insert can be split into multiple partitions and parts. Consider that you have the data partitioned by an hour or a day, and your insert, it's actually spun across multiple hours and multiple days. And then you inevitably will have multiple partitions to insert with a single statement. Certainly columns are sorted based on a primary key and based on table order, and primary key is calculated. Then columns are compressed and are written to the disk, but first they are written into the temporary, subtemporary directory or directories, and every column may require several files in a single part. And once all columns are written in this temporary directory, this is being renamed to the real one and available for your queries. So there are quite a lot of steps here. Some steps involve CPU, and other steps involve storage. Based on those steps, we can define general considerations that are important for fast inserts. So first and foremost, use bigger blocks because there is a lot of overhead on a single insert. So all this parsing, preparing columns, and writing columns to disk, and multiple columns per insert, that is quite a lot of overhead. So if you use bigger blocks, then this overhead, which is pretty much constant for a single insert statement, it doesn't increase linearly. Second important principle is that do not insert too often. So ClickHouse is not a LTP database for sure, and it's not designed for single row inserts that are generated 100 times per second. You can insert a single record, no problem, but due to overhead, you cannot insert it too often because this overhead will be increasing and increasing. Another important consideration is compression. Sometimes some users, in order to save on disk space, they may want to enable very aggressive compression. ClickHouse supports GSTD up to level 22, and you can certainly do it, but after that, you might be quite confused by decreased insert performance. So ClickHouse will have to apply this compression on inserts and later on merges and queries, but that will slow down your insert performance considerably. In fact, it's possible in ClickHouse to configure layered compression when you have less aggressive compression for small data, small parts, and more aggressive for the bigger parts. Another important consideration is partitioning. So as I mentioned on the previous slide, if you have multiple partitions inside one insert, one block of inserted data, then it may result in multiple different parts to be written on this disk, and every part has a lot of files because of columns. So it's not a good idea to partition by second, for example, because it will definitely generate a lot of partitions. It's also not a good idea to do some random generators using your tests that generate a lot of random partitions. For example, we in our practice we've got a case recently when the table has been designed quite right using daily partitioning, but when the customer generated test data, they generated inserts that contained random day, and therefore every insert resulted in several hundreds of partitions. It will never happen in the real life, because in real life the data is coming for the current day or day before, but in tests they got very mixed results and were kind of confused with ClickHouse performance. And two other considerations are related to cluster setup. Inserts in ClickHouse, they communicate with the keeper. So they write metadata in the keeper, and therefore, if the keeper is not close to the insertion process, then insert latency may decrease. So inserts needs to be close to the keeper as much as possible. And the last consideration here is that ClickHouse has a lot of asynchronous operations internally, and this is by design because ClickHouse is designed to be as fast as possible, and asynchronous operations, they allowed ClickHouse to be faster. But on the flip side, this is less reliable. So there is always a trade-off between performance and reliability, and you can trade one for another or vice versa. And ClickHouse has a lot of fine-tuning settings to do this, to configure this trade-off. Now let's look into some particular techniques that can reduce overhead during our insert to get better performance. First is buffer tables. And buffer tables, they can be used if you have a lot of ingester agents that you cannot ingest or insert small amount of data, and you cannot buffer or aggregate it on application side. In this, I will show you in a second. You can set up a buffer table in ClickHouse that will collect the data from those multiple inserts and flush using some pre-configured thresholds. And another technique which emerged in ClickHouse not too far ago is a polymorphic merge tree parse. This allows to store small inserts more efficiently both in terms of storage communication, in terms of data processing, and so on. So buffer tables. Once again, the use case is where we have multiple small inserts coming into the system. In this case, you set up this buffer table, which is connected to a particular destination table, in this case, merge tree table. It collects those small inserts, and when size or time threshold is hit, it flushes the data to your merge tree table. On the query side, you can query data from the destination table, but this data wouldn't contain your most recently inserted data to the buffer. Contrary, if you query from the buffer table, then ClickHouse would automatically merge data both from buffer and from destination table, and you will have the full data with most recent data included. This is a good approach, and it exists in ClickHouse for years, but the problem is that the data can be lost on hard restart. So if server has been restarted, then everything that is in buffer can be lost. So while it's good enough, it doesn't fit some user expectations. Another technique is polymorphic parts, and polymorphic parts consists of two new features. One feature, which exists since ClickHouse 20.3, is compact parts. And in order to understand what it is, let's look into how part is stored in a file system. So white parts, which are default and they exist in ClickHouse for years, this is our columnar structure where every part of the data is stored in multiple files. There is one index file, there are some metadata files, and for every column, there are at least two files. Files with data and files with marks, which is called mark2 in the current ClickHouse version. Compact parts, which is quite a new feature, they allow to start the same data but in a less number of files. Index is stored as before, but data, binary, and mark file, those files now store all columns altogether. Internally, it still maintains the columnar structure, but on a file system level, this is just a single or two files. This is an example. This is a data from airline dataset, which contains 109 columns in a table. And the white part, it takes 224 files to store, which is quite a big number. While compact parts, it only takes 8 files. So you can see the difference is tremendous. And this pays out pretty well in insert time as well. So just to summarize the compact part design, this is a single file or a couple of files, but the internal structure is still columnar, and it's not row store, it's just different way to store the data. And the main purpose is to reduce the file system overhead, especially on small inserts. The threshold is controlled by a number of settings. You can configure threshold by bytes or by rows. In ClickHouse, this feature first has been enabled for system tables. In 20.3, it has been enabled for system tables, and that was kind of testing in the field, because system tables, they always exist. ClickHouse always writes a lot of data to its system tables, and that was a proof from ClickHouse perspective that this feature is stable. And since ClickHouse version 20.8, this is enabled by default. So by default, right now, all parts that are below 10 megabytes in size, they're stored in a compact form. So you don't need to configure anything. The next addition to the gang was memory parts. This is yet another extension to the model. And memory parts, they allow ClickHouse to store even smaller amounts of data in memory without writing it to the disk. And in order to guarantee reliability, ClickHouse has write-ahead lock. So with memory parts, even if those stored in memory, if there is a failure, ClickHouse can replay data or restore data from write-ahead lock after restart, so the data is secure. And the typical pipeline looks like this. So very small inserts goes to memory. Then after inserts go bigger during the merge process, for example, they go to compact parts, and later on compact parts are merged to the bigger wide parts, which are most efficient for queries. With memory and compact parts, queries are also good, those structures are not as efficient for queries as wide parse, but since we only keep small amounts of data here, it's not an issue at all. So next big topic is insert atomicity. If we line out user expectations, then users expect that inserts writes all the data completely or aborts. Inserts writes all the data to all dependent objects, materialities, and so on, or aborts. Inserts writes to all distributed and replicated table or aborts. So this is what users would like to expect or would expect, but there are no transactions in ClickHouse, and therefore it's not trivial to guarantee these expectations. So we need to do some extra steps or extra configuration actions in order to do this. So let's start again with a single table. Consider we have insert, which is common to a single ClickHouse, and as I explained earlier, the data is parsed and written in blocks, parts, and it's interesting that those blocks are written as soon as they are ready. So if, for example, we have insert for 10 million rows, then ClickHouse would split it into 9 or 10 parts automatically, and I will explain in a bit why. And it will write first 1 million row as a part, then second million row, then third million row, and then if anything happens to the server, you will have a partial insert. So some of the data has been written and some of the data has been not. So the main principle here is that we need to ensure that there is a single part in insert. Or if we cannot do that, then it's very hard to guarantee atomicity. So how we can make insert to write a single part? First, if you insert using ClickHouse client, then insert block is controlled by max insert block size parameter, which is default to 1 million rows. So that means ClickHouse will split data to 1 million rows parts. So in order to insert bigger blocks and guarantee atomicity, you need to increase this block size. You can increase it to 10 million rows or more, but beware of memory. So for atomicity, ClickHouse needs to put everything in the memory first and then write to the table. So if you're trying to insert a billion rows and would like to make it in a single part, then you probably don't have enough RAM for that. Another approach which is possible is to insert using in a temporary table. And from this temporary table, then run insert select to a permanent table. In this case, however, the chunks that data can be split into is controlled by several different parameters. First parameter is max block size, and this is how ClickHouse reads the data from the table. So this is kind of select part of the equation. And then there are two parameters, min insert block size rows and min insert block size bytes, and ClickHouse will try to merge data into those amounts before writing a chunk of data to the storage. So if you want to do an atomic insert here, then you need to adjust those two parameters. Same parameters, they also are used when inserts are going via HTTP. It's kind of counterintuitive, but ClickHouse client and HTTP interface, they require different parameters for atomicity. The reason is that ClickHouse client builds columnar data by itself and then sends to the client, but when data come in by HTTP, everything is done by a server. Another possible problem is parallel parsing. So for text formats, ClickHouse currently supports parallel parsing, and when data is parsed in parallel, ClickHouse may write it in multiple parts as well, which is again kind of might get you in a surprise. And last but not least is max insert threads parameter, which is designed for fast parallel insert selects. So if you run an insert select from one table to another, then max insert threads can give you much better performance. So if you set it to 16, for example, and you have 16 cores, then you get almost linear performance increase. But on the flip side, every thread will be writing a different part, which again may result in some inconsistency if something happens at the middle of your insert select statement. After insert has been complete, it doesn't mean that your data is already in the storage, thanks to host page cache. And in recent ClickHouse versions, ClickHouse development team added a lot of different settings for managing fsync behavior. So when to do fsync, so at what point ClickHouse should call fsync, and this is something to look into and probably do some experiments. The problem with those settings is that first you need to understand very well the Linux behavior and what to expect if you turn something on and off, because from one side it can result in some additional latency, and from another side sometimes turning those settings on and off they don't help. There are two good articles that you can find on internet. First is Files are Hard, and second is about PostgreSQL that explain that even if you have fsync, it doesn't mean that your data has been written. So apparently Linux is not very reliable in terms of communication to the storage, and this is something that people have to deal with. With ClickHouse, you can always have a replica, and that will give you much better guarantees of reliability than trying to tune this fsync behavior and to make sure that the data has been written. We will get to replication a bit later, but before then, let's consider a couple of other complications. One complication is materialized views. If you write to the table and you have several materialized views, then under the hood, materialized views are executed sequentially in alphabetical order. And there is no atomicity guarantee. So if one materialized view fails for whatever reason, then there is abort, but abort only for parts of the data, not for all. So you may easily get some inconsistent behavior when your table and your materialized views are out of sync. So what we can do here? First, there are two partial workarounds that reduces probability of failure but don't fix it 100%. First is parallel view processing setting, which run all views in parallel. So if anything fails, there is a bigger chance that no view has been written yet. Second recommendation is not to use cascades. So in the picture here, I have materialized view 3 sourced from materialized view 1, and this is even less reliable than having multiple materialized views attached to one table. So instead of this setup, I would probably need to move MV3 directly to my table and have just 3 materialized views attached to the table. By the way, ClickHouse doesn't have any limitation on number of materialized views attached to a single table. It's just additional overhead and possible reliability concern. The good news is that materialized use transactions are coming next year, so we actually have them in the roadmap. Next thing, how can we do distributed table insert? If we insert reliable, if we insert to single shard, then the data is split by sharding key. If we insert to distributed table, the data is split by sharding key and then stored locally in so-called distribution queue. Once the data is stored locally, a client is acknowledged that everything is good and your insert is successful, but this distribution queue is processed asynchronously. So if there is a hard reset on shard 1, then there is a possible data loss. What are workarounds? Our main recommendation is do inserts locally and don't insert to distributed table, but it's not always possible. If you have to insert to distributed table, then there is an insert distributed sync parameter, which you can turn on. And in this case, ClickHouse will write to shards in a synchronous manner and acknowledge the client only if all shards have been written successfully. And there is also timeout to control for how long ClickHouse would wait until all shards acknowledge the data right. Replicated table insert. It's also not very trivial. When the data is written to the table and part is written locally, it is registered in Zookeeper. After the part is written locally and registered in Zookeeper, client gets an acknowledgement that insert has been successful. And only then data is fetched asynchronously by replica or replicas. So if there is a hard reset on shard 1, even with replication, we may have a data loss. The workaround here is insert quorum. You can set insert quorum equals 2, and in this case, ClickHouse will write to 2 replicas and make sure that the data has been inserted at least at 2 replicas before acknowledging the client. That gives you much better consistency guarantee, but at the cost of performance. There is always a trade-off, because writing to 2 replicas, it's slower than writing locally to a single one. Kafka ingest. If you use Kafka, there are even more ways to fail. You can fail because Kafka requires one more materialized view to process. So there is first Kafka engine that is subscribed to the topic. There is some internal buffer. So you can think of Kafka engine as a buffer table. Then there is a materialized view that tries to merge tree table or replicated merge tree table. If you have replica, you may have materialized views attached to this table for some other reasons like aggregates. And there are many ways to fail here. The good thing is that Kafka kind of guarantees exactly one semantic for consumer, and you can turn it on in the ClickHouse in configuration. In this case, there is a guarantee that a Kafka engine fetches the data once and only once. The later part of the pipeline is the same as with our ordinary insert. So you need to make sure that you have insert quorum for replica. You need to make sure that you have proper setup of materialized views for distributed tables and so on and so forth. So with EOS guarantees, Kafka ingests are reliable in ClickHouse. There are several things that make this a bit more complicated, like you may have multiple topics, you may have multiple partitions per topic with partition rebalance, and so on and so forth. But more or less, it is already solved in ClickHouse. So we think that Kafka ingest is pretty much reliable. So just to summarize best practices for reliability, this is the following. Don't use buffer tables if you don't have to, and the compact and memory parts, they do the job better. Try to make sure that insert generate single part if possible. If you go to multiple parts, then there is no easy way to guarantee atomicity. Insert distributed sync and insert quorum can help with synchronization for distributed inserts. Don't use cascading medialized views, and you can apply durability setting if you understand them. The next and last topic for today is the duplication. And let's start with the question why duplicates are ever possible at all. The most obvious scenario is when we retry failed insert. For example, we try to insert and we get an error message. But sometimes we're not sure if this error message because insert failed or network failed or my client failed, and the client library may want to retry it. And if the previous insert was successful, then we'll get a duplicate data. Another possible reason is some collision in message bus. For example, if Kafka rebalances, especially in some older versions of ClickHouse, it was possible that the data has been inserted to Kafka table twice, and since every Kafka table processes them independently, we could get duplicates. And also user errors. So if you run your import twice, you can get duplicate data. But the problem is that there are no unique keys and unique constraints in ClickHouse, so there is no good way to guarantee, on the database level at least, that there are no duplicates. But there are some workarounds. First, there is a block level duplication. It is built for retry scenario. What ClickHouse does, it keeps history of block hashes per table. And if insert has a hash that matches the stored block in the history, then this insert is ignored completely and silently, so no error. So if you make an insert in replicated table, then you insert exactly the same data second time, then then the insert is ignored. Sometimes it results in funny things. For example, if you develop some tests and insert data in tests, you cannot insert same value twice in a replicated table if you insert a single row, because it will be deduplicated automatically. This feature only works for replicated tables so far. There is a common development for non-replicated table, and we expect it to be completed in the next quarter. So for non-replicated tables, this history of block hashes will be stored locally. For replicated tables, it's stored certainly in Zookeeper. And there are several settings that control this behavior, like a deduplication window, which is 100 by default, deduplication window seconds, this is time, right? And deduplicate blocks independent materialized views. This is useful when there are materialized views attached. So it makes sure that ClickHouse, if you insert in the table and there is a duplicate at the table level, it still continues to apply the insert to all materialized views in the chain. Without this setting, ClickHouse would return immediately and silently, and materialized views wouldn't be affected. Another technique that ClickHouse has for deduplication is replacing merge tree. What replacing merge tree does, it eventually removes duplicates. So you may define the primary key, and this is your kind of unique key. But ClickHouse doesn't force uniqueness on insert and can only eventually remove duplicates during the merge, or you can force it with optimized final to do this deduplication on the data, and this is maybe quite expensive and costly operation, or you can select final, which will do deduplication in the query time. This is good for the cases when consistency of duplicates is not that important, but you want to make sure that eventually you may have deduplicated data. Select final is slow for aggregate queries. So consider you have a table with billions of rows, then select final from that table may be quite slow. But if you have a table with some, and you filter by key column, then it is very fast because ClickHouse has to do this deduplication only for the data which is subject to where condition, and it can be very, very fast. In addition to tools on the database level, you can do something on application level, which we call logical deduplication. This is good for scenario when you have a natural unique ID in the table, or you can calculate a unique hash. And this works like the following. You first insert to some temporary table. It could be temporary table, could be some intermediate table, whatever doesn't mean. That doesn't matter. And then when you insert select from this temporary table to your permanent table, you add extra where condition, and you check explicitly that the data doesn't exist already in your destination table. This where ID not in may be quite heavy, but you can make it fast. First, your table in the temporary table, your data in the temporary table is relatively small, right? And second, you can apply duplication window for 1 hour, 1 day, or whatever that can make it more efficient. You can even build a dedicated materialized view that would keep the track of inserted IDs, and that way make it faster to do such a check. Another alternative to the temporary table is to use a null engine. A null engine is an interesting feature in ClickHouse that allows you to insert data but don't store. It's at the same time it fires all materialized views attached. So if you insert to null table, and then you can use this materialized view with where ID not in condition, that would move the data to your permanent table. One of our engineers, he designed a bulletproof deduplication for Kafka, and I don't mean you to understand this excellent diagram, but you can scan this QR code and navigate to the bigger picture and try to understand this logic. So this approach actually considers that with Kafka and with rebalance of partitions, it's possible that your data may reach to different servers due to rebalance. So for deduplication, you have to do some sort of distributed table. So this is not, at this stage, it's not trivial anymore, but you still can make it to work. And this diagram explains how. We're almost done. A few more topics to discuss. First, how we can find duplicates in a big table. Consider if you have a table with billions of rows or trillions of rows, and how can you find if you have duplicates or not? And you can try to group by your hash, right? Hash here is some unique identifier, and try to find the hashes that have more than one occurrence, and probably some timestamp in order to locate this data better. But if you have billions of unique rows, then it may be very slow and it might take a lot of RAM. An interesting approach that has been suggested by one of our clients is to use neighbor function. And when you use neighbor function, you can compare the value of the column to the value of the row to the value of the previous row. And if those rows match, then there is a duplicate. And the beauty of this approach is that it can be done in a single pass and it requires much less memory. The caveat here, however, is that neighbor function, it works inside blocks, and blocks, a block is controlled by max block size, so it works not on all your table, but on a part of your table. So on the border of the blocks, there may be inconsistency, but it's easy to locate. So with this approach, it's pretty fast to detect duplicates in a table, especially in a sum window. If you have duplicates, right, ClickHouse has a way to deduplicate. There is a special statement, optimize deduplicate, that fully resorts your table, removing duplicates, and it considers duplicates the full row. So if there is identical row with all values are identical, then with all columns are identical, those rows will be removed and only one is left. We have a feature currently in development is to implement deduplication on a subset of columns. So you may have your rows which vary only by a timestamp, for example, but all other columns are the same. With this optimized deduplicate by, you can actually deduplicate by all columns except your timestamp column, for example, or you can deduplicate by some subset of columns and so on. This feature is coming in the next ClickHouse version. Final words. As all we know, ClickHouse is very fast and reliable, but sometimes bad things happen. So proper schema design is probably the first thing and the most important thing for performance and reliability. So this is the first thing to pay attention to. Default ClickHouse settings, they are tuned for performance. So ClickHouse is all configured for performance sake, but not for reliability. So if you want to get more reliability guarantees, you have to change some settings. Atomicity requires careful attention in design. And this is actually a painful problem in ClickHouse, but we're going to work on that next year. First thing to arrive is block deduplication for non-replicated tables, and this is going to be delivered in Q1. Second thing is transactional materialized views updates, which would guarantee that all materialized views are updated or not updated together with your main table. This thing we expect something in Q2, and after that, we expect that transactional multi-inserts are possible. So you may configure to have multiple inserts, and all of them are successful or aborted. Those are some useful links. Probably you know all of them already. ClickHouse website, ClickHouse channel, and so on and so forth. Thank you. And I'll be happy to answer questions if Robert hasn't answered all of them yet.
I haven't, and there's some great ones that are queued up for you, Alexander. So first of all, thank you so much for that talk. And by the way, I see a lot of folks who are Altinity customers. I'd like to give you a special welcome. We also welcome everybody else as well, but it's great to see friends on the call and to hear some of the questions you've been asking. So let me queue up one which came up twice. And that is, are there any performance impacts for compact parts?
Performance impact is on the positive. So on insert, it works faster. On select, compact parts is slightly less efficient, but since we only store small amounts of data, you wouldn't notice it in regular queries.
Okay, great. Let's see. There was another question that came out of the chat. What's the lifetime of the block hashes? Does it persist across server restart?
Yes, it does, because it's stored in a Zookeeper. By default, ClickHouse keeps 100 blocks per table, and you can configure it per table. And also it stores at something for 7 days or 14 days, something like that. So quite long time.
Yeah, and actually one support question that comes up periodically is people will insert test data into a replicated table, And if you repeat the insert, only the first one goes in, the next one is ignored. So we occasionally get support questions like, hey, why is ClickHouse deleting my data? And it's just because deduplication is kicking in. Here's a good one. Is it possible to force a buffer to flush to its destination table independent of the threshold set in the buffer table config?
Yes, there is a system flush something statement, I guess, that you can run in order to force a buffer flush.
Okay, great. Next question, from which version did parallel view processing become available?
Oh, this is quite old one. It's probably from 2019. I don't remember exactly, but it's quite an old one.
Okay, so it should be any 20, and it's stable in
Yes.
all 20.x releases.
Yes.
Okay, great. So if you're even moderately up to date, you should be able to get that. Great. Next one. How this is the how does compact parts affect performance? We already got that. Here's a question on the this was slightly off topic, but again related to fast ways to load data. So S3 table functions. Is it possible to execute asynchronously to read from the S3 table function asynchronously? And that's question number one. And is it reliable in the sense that it will retry if one of the read operations on a large glob fails?
No, it is not. I mean, there is no async way to fetch data from S3 right now. And if Glob fails, I don't know what to do. So it's
I think it just
yeah. So it's not, because but it's pretty reliable. So what we did recently, we were experimenting with this Texi data set, which is our standard mouse, right, for experiments. And this data set, it takes only 4 minutes to fetch from S3, and this is something like 100 gigs or 70 gigs, quite
right.
big one.
And
what you can do asynchronously is to write to S3. If you configure S3 storage for your merged table, then you can configure ClickHouse to move data to S3 in the background, and this is done asynchronously in the background.
Cool. Yeah, and one of the points that I think is useful to make is we've told you about some bad things that can happen. I think overall, looking at all the ClickHouse installations that we know about, and we have, we've worked with well over 100 customers over and some really big installations. Most of these problems that we're describing are rare. So so that's something, but they do happen, and that's why that's why we want to make sure that that you understand how to get around them, and also to be clear that there's a roadmap to ensure that they cannot happen at all. So I just want to be clear about that. And there's the reason I thought about that is a related question, Alexander, is alter delete operations stable? Sometimes we need to delete rows from our analytic database.
Yes, alter delete is stable. This is something that stabilized over 2020 quite a lot. But if you have a huge database, that might be quite a heavy operation, even in the background, especially if you have big partitions, and the ClickHouse will have to resort quite a lot of data during this delete.
Yeah.
So that's okay to use, but this is quite an expensive thing. We actually have a roadmap item to implement lightweight deletes when ClickHouse would mark data for deletion first, and it's immediately deleted for the users that query the data. But the delete itself will be executed later in the background when time permits.
Yeah, that's a great point. And if anybody on the call has interest in that feature, it comes up a lot in GDPR and data privacy conversations. Please feel free to reach out to us directly if you're interested in helping us push that one along. It's a really important feature. Here's another one. Back to buffer tables. What's the best way to confirm that a buffer table is empty? Querying the buffer in the destination table and confirming the row counts are equal?
Yes, maybe that's the best way. Yeah.
Okay. Here's one. Which solutions, if any, to deduplication do you consider best practice for a large dimensional data warehouse that is inserted continuously, but is occasionally updated, like maybe less than 0.1% of workload is updates?
It depends on what is updated. So if you have a large multi-dimensional data warehouse, you typically have two types of tables. You have your so-called insert-only tables with some transactional data, events data, and so on. And this data is usually is not updated at all, right? Sometimes if or some data corruption, you may need to reload some sort of rows, but not update. And from the other side, you have your dimension tables that are slowly changing dimensions, and sometimes they may be updated. So those dimensions, actually, the best way is to use ClickHouse dictionaries rather than ClickHouse tables. And in this case, updates are handled on the other database side, and ClickHouse just maintains the up-to-date copy in memory of this data. But if you still need to update on ClickHouse, then replacing merge tree is good for such use cases because those dimensional tables are typically not very huge, and you can run optimize table for them. You can also use join any if you need to join those tables in your queries. ClickHouse has a join extension which is any join, and in this case, it will join a single row even if there are duplicates.
Okay, I hope that covered it. A related question, is there any way to know when the tables are consistent again after an update? And when I say update in the ClickHouse world, that means reinserting a row with the same unique key as a pre-existing row. So sort of a follow-on.
So if it's a question about replacing merge tree, then that's a good one. I don't know from the top of my head.
Yeah. And
so you can force it, right? So you can force optimize table, and if it's completed, you can be sure that the data is updated.
Yeah. I would have said, what's it worth to you to know? Because it's sort of like, yes, you can find this out, but are you willing to pay for a scan? And if you're replicating, if you're sharded, finding out whether this is finding out the answer may be expensive. That's really the big trade-off that you get with with handling duplicates at scale.
Yes, and also I would like to add that if you insert a single row, right, if you want to update a single row and you insert a single row in a replacement merge tree, then if you don't do anything, it will never be merged to the other rows, and it will never be updated unless you run this optimized duplicate. Because ClickHouse, for ClickHouse, consider you have a huge table with a lot of data, and you insert a single row, and merging everything with a single row is expensive operation. ClickHouse wouldn't do that by itself, but you can always force it to do.
Right. Question: Can you run alter delete on a single row or only a partition?
On a single row, yeah, sure.
Yeah.
Any where condition is possible for alter delete.
And for partitions, actually, those are the best things to delete. You can just drop them, and that's that's a super fast operation. Okay, let's see. So I think we have, I think we've gotten to the end of the questions. The final question, which is sort of a follow-on, is that optimized force is reliable. Is optimized force reliable if you wait for it to complete?
Optimized final, yes.
Optimized final, that's what
yes, it's reliable, and this is synchronous. You ClickHouse will force you to wait until completion.
Yeah. Great. Well, some really excellent questions here. I hope we got to all of them. Let me just double check the chat. We're right at time, so this is perfect. I think what we'll go ahead and do. Oh, there's one final question. We'll take one last question and then we have to go. So, what if we run alter table and have to add columns to merge tree or replicated merge tree? New data will have new columns and previous data won't have any in the newly added columns. What's the best way to approach? Use alter table?
Yes, just alter table. So this is a very fast operation and just changes metadata. And once a new data comes, it will be written to this new columns, and all columns will be considered to have default values.
Great. All right, we're going to call it a day. We have to close up shop, but thank you so much for attending. Alexander, thanks for a really great talk. And thanks for the wonderful questions. We really appreciate them. If you have more questions, don't hesitate to contact us. We do this for a living and we love working with this. So thank you very much. Once again, the recording and the slide links will be sent to you in an email once we have them ourselves. So have a great day and talk to you soon.
Thank you, Robert. Thank you, everybody. Bye-bye.
Bye, everybody.